What's up, guys? Chapter 5.1 is exponential functions, which we deal with most of the time in Chapter 5. So this whole chapter is pretty much going to be exponential and logarithmic functions. They're not as bad as they sound. I really like exponential and logarithmic functions. A lot of people come into college, they don't have too much experience with them, even though you're supposed to review them in high school. But we're going to make our way through them. I don't think they're that bad. A few little rules you have to know here and there. If you can get and master those rules, it's really not that hard. It's just keeping track of your rules. Some of the stuff towards the end will get a little more in depth, and then we'll actually work with some stuff on the calculator as well. So let's start this out with the first definition. If b is a positive real number, or b is not equal to 1, then the function f of x equals b raised to the x is an exponential function. The constant b is called the base of the function, and the variable x is the exponent. Now we're going to graph y equals 1.5 raised to the x versus y equals 12 raised to the x. Okay? So if we come over here to our TI, we're going to graph 1.5 raised to the x. And we're going to graph 12 raised to the x as well. So if we graph both of those, we need to adjust our window. I'm going to zoom standard because the window I had there was not very good. So if you'll notice, blue is the first one. That's 1.5 raised to the x. This is the 12 raised to the x here for the red one. If you notice, 12 raised to the x increases much faster, and it makes sense. Okay, 1.5 to the 0 power is all obviously going to be 1. That's where both lines meet. Anything raised to 0 is 1. But once you start raising it, 1.5 to the 1 is just 1.5, but 12 to the 1 is 12. Now 1.5 raised or squared is going to be somewhere between, say, 3 and 4. So it increases really slow. But if you look at 12 squared is 144. So it's way up there once you go over 2. So the bigger your base number is, the quicker it's going to accelerate upwards. And that's essentially what your note here says. It says, note, both are increasing. However, 12 raised to the x increases faster. Now, let's graph y equals 1/3 raised to the x versus y equals 3 raised to the negative x. Okay, so if I come over here, y equals, clear this one out, put my parentheses in, 1/3 x, and the second one is 3, oops, let's clear this out, 3 raised to the negative x. Now if we graph those, there's your first one, there's your second one. If you notice, they're the exact same line. Now why is that the case? It's the case because they're the exact same function. You have to remember your rule, which states that if I have a negative exponent, all I have to do if I want to get rid of that negative exponent is essentially flip the inside. So all this is, 1/3 is the opposite of 3. You flip it and you get the same thing. Okay, what you'll also notice is they are also decreasing. So here, when we had the other ones are increasing, these are decreasing, and that's really important. So if you have a fraction, or if you have a negative exponent, then what you're going to wind up with is something that's decreasing. But if you have something that's not a fraction, or not a fraction between 0 and 1, and is basically a whole number, then it's going to be increasing. Okay, so we've got a bunch of these rules here, and those are kind of incorporated in it. So the graphs of exponential functions. The equation looks like y equals b raised to the x. The x-intercept, you don't have one. It approaches the x-axis. Don't believe me? Let's go look at the line. It gets really close to the x-axis, and it might look like it's on the x-axis, but it's actually just really close, and it never actually touches the x-axis. So you don't have an x-intercept. Your y-intercept is 0, 1. Your domain, it's going to be all real numbers. Your range is all real numbers where y is greater than 0. Because if you look at your graph, your line never goes below that x-axis. Therefore, your y's are never negative. They're never less than 0. Alright. Your horizontal asymptote is the x-axis. An asymptote is just the line that you approach. Here, your line's approaching the x-axis. Okay. Shape, you have an increasing function when this b your base, is greater than 1. You have a decreasing function when y equals b raised to the x and b is between 0 and 1, or if y equals b to the negative x when b is greater than 1. So if you have a negative exponent and your b is greater than 1, you've got a decreasing function, or if your base here is between 0 and 1, you have a decreasing function as well. So, continuing on. If you want to see an example of each, it was just the 2 examples of above. Okay, so let's look at the transformations of graphs of exponential functions. So if we look at a vertical shift, g of x equals b raised to the x plus k, that means the graph is shifted up k units if k is positive, and down the absolute value of k units if k is negative. So it works just like the other ones. Outside, we move up and down. If it's inside, and by inside I mean inside with the x, then it's shifted left or right. So the graph is shifted, horizontal shift, h units, right if h is positive. So we've got b raised to the x minus h. So if you've got a negative up here, so if it's an x minus h, we're actually going to move right. If it's an x plus h, we're going to move left. And that's essentially what this says, just in a little bit different wording. It's saying that using this format, b raised to the x minus h, if h is positive, then you're going to move right. Using this format, if h is negative, you're going to move left. Okay? Whichever one of those works in your mind. A lot of students like to think about it as, okay, if I look at this and I've got a negative h up here, that means I move right. If I look up here and I have a positive right here, then I move left. And that's fine. Other students like to think of it as, okay, if I have this format, b to the x minus h, and that h is positive, I move right. If that h is negative, I move left. Okay? Either one works. Just pick one and keep it straight. Now we can also look at the reflection across the x-axis. So if we want to reflect across the x-axis, then g of x equals negative b raised to the x. If we want to reflect across the y-axis, then g of x equals b to the negative x. It's pretty simple. If we want a vertical stretch or compress, what we're looking at here, we've got g of x equals a times b to the x. If a is, or the absolute value of a is greater than 1, we're stretching. If the absolute value of a is less than 1, we're compressing. Just rules you got to keep in track of. If we're looking at a horizontal stretch or compress, it's the same thing. We've got, or it's close to the same thing. Here we've got a b raised to the a times x. So if we're stretching horizontally or compressing horizontally, we're messing with the x. If we're stretching vertically, we're messing with the b. Graph is stretched horizontally if the absolute value of a is less than 1, and the graph is horizontally compressed if the absolute value of a is greater than 1. Okay, so we finally got some examples here. So we've got y equals 3 raised to the x, and we need to explain how each graph compares to this original function. So I'm going to take these to the board so that you can more clearly see how these examples work with each other. Keep your notes clear by, or right by you, so that you can kind of have the rules next to you to go back and confer with. But keep those nearby, and we'll go through each one of these examples, and I feel like you'll get a better understanding of how it works. After we do these examples, we will also graph them to show you exactly how they work. Alright guys, so our original function y equals 3 raised to the x. A says y equals 3 raised to the x minus 4. We need to figure out how this is shifted. Okay, it's with the x, so it's on the inside. Therefore, we're moving left or right. Okay, so we've got x minus 4. This is really the piece we're looking at. So it's moved right 4 units. Okay, if it was a positive 4, we move left 4 units. Okay, here y equals 2 plus 3 to the x minus 4. So we've got two things happening here, right? So we've actually shifted right 4 units just like we did here with this. So we can go ahead and write that one. Right 4 units, comma. We have this 2 out here, okay? It's a positive 2. Therefore, we shift up 2 units. Easy enough. So this causes us to shift up 2 units. If it was negative, we'd shift down. C. We have 5 times 3 to the x. So 3 to the x is all the same, but we're multiplying on the outside. So what we have is we have a vertical stretch. By a factor of 5. Okay? Because it's on the outside, it's right here, it's associating with this 3, it's not associating with the x. We're going to have a vertical stretch by a factor of 5. It's that simple. If you know your rules, these should come out really, really easy. You just got to take a little bit, memorize, and figure them out. You'll be good to go. Alright, now I told you I would show it to you on the graph as well. So my initial function is y equals 3 raised to the x. Clear all these out. Y equals 3 raised to the x. My second function was y equals 3 raised to the x minus 4. So if we graph that initial function, you can notice this function is clearly shifted right 4 units. If we look at our second function, so I'm going to clear this one out and put our second function in, we get 2 plus 3 raised to the x minus 4. Okay, we're going to graph it. You notice it's moved right 4 units and it's moved up 2 units. Okay, now let's graph that last function and compare it. That was 5 times 3 raised to the x. We graph it, initial function, and it's stretched. Think about stretched as grabbing this end piece here and pulling up. If you pulled it up, it would stretch and pull that way. So you can see it's stretched. It's not clear to see by which factor. You can't really look at the graph and say, oh, that's clearly a factor of 5, but if you look at the equation, you can clearly see it by a factor of 5. Alright, now let's move on to the next part. So, the next example says use a table from x equals -3 to x equals 3 to determine how the graphs of y equals x, or y equals 3 raised to the 2x, and y equals 3 raised to the 1/2 x are related to y equals 3 raised to the x. So let's go to the board real quick, and we'll make a table from x equals -3 to x equals 3 and compare these graphs. So here's our chart. We've got x values from -3 to 3. We've got a 3 raised to the x, 3 raised to the 2x, and 3 raised to the 1/2 x. So what we can see, and I'll show you how to do this on the calculator where you can look at all the values at one time. But what we'll see here, when I plug in -3 here, 3 to the -3 is actually 1 over 27. Okay, 3 cubed is 27 because of the negative in the exponent. It goes to the bottom. Okay, 3 to the -2 is 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 3 to the 3rd is 27. Okay, so if I plug this -3 in here, 3 raised to the 2 times -3 is going to be the same thing as 3 raised to the -6. 3 raised to the 6 is 729. It goes on the bottom. It goes 1 over 729 because it's negative. Okay, same thing here. 2 times 2 is 4. 3 raised to the 4 is 81. It's on the bottom because of the negative in the exponent. Okay, and it just works its way down. So what I could tell comparing this one to this one is that obviously this factor right here on the small side, on the negative side of things, makes this number much smaller than this number, because 1 over 729 is much smaller than 1 over 27. When I get to 0, it's the same thing. And then when I go over 0 into the positive numbers, what I notice is that this number is way bigger than this number. This number is bigger than this one number is bigger than this one. Okay. If I'm comparing these two, some of these didn't wind up being really nice, neat fractions. If I'm comparing these to these, and I look at it, okay, let's look at this one. This one right here is a bigger one than this one. Let's see, this one's the same. If we're comparing these, this one's bigger. So you can tell that this is a slower increasing function than this one. This one's a faster increasing function than this one. And that's what I want you to see here. I'll show you real quick how to put this in on your calculator and look at the numbers where you don't have to do it all by hand. and they'll all pop out for you. They won't all be fractions, they'll be all decimals, but you'll still be able to see the value of the number, which is what is important here. Alright, so I got that initial function in 3 to the x. In y2, I'm going to put 3 raised to the 2x. And in y3, I'm going to put 3 raised to the 1/2 x. Now I'm going to show you how to get these values and any other values you might need right from your calculator. So instead of going graph, I'm going to go second graph, which will bring you to the table. So second graph or second table. And what I see here is I got my function y1, y2, and y3. And I've got my x values here. So if I wanted to figure out what the x values are from -3 to 3, I can just look at my table. For that y1, which was 3 to the x, I've got all those values here. Like I said, they're not going to be nice, neat fractions like what we found on the board, but they are available for you, okay, in decimals. Here are the values of 3 raised to the 2x, and here are the values of 3 to the 1/2 x. So you can see the same thing. This function increases faster than this function increases slower than that function. Alright, so let's look at exponential growth models. So for this equation, I've got y equals a times b raised to the k times x, where b is greater than 1, a is greater than 0, and k is also greater than 0. Here we also don't have an x-intercept. Our y-intercept is going to be 0a. So 0 and whatever this a is in front is going to be our y-intercept. It's where it's going to hit the y-axis. Okay. So if you can figure out what that constant a is out front all by itself, you'll have the y-intercept. Okay. The domain is going to be all real numbers. The range is going to be all real numbers as long as y is greater than 0. The horizontal asymptote is still your x-axis, and the shape is increasing on the domain and concave up. Continue on in your notes. We have this example. It says suppose that inflation is predicted to average 4% per year for each year from 2012 to 2025. This means that an item that costs $10,000 one year will cost $10,000 times 1.04 the next year, and $10,000 times 1.04 times 1.04, which equals $10,000 times 1.04 squared the following year. Write the function that gives the cost of a $10,000 item t years after 2012. Alright, so if I read B, it says graph the growth model found in part A for t equals 0 to t equals 13. C says if an item costs $10,000 in 2012, use the model to predict its cost in 2025. We will do all of these and then get on to the next example. But let's go to the board first and figure out this function that gives $10,000 of an item t years after 2012. Alright, so we got an item that costs $10,000 in year 0. So the very first year you buy it, year 0, it costs $10,000. Year 1, it costs $10,000 times 1.04. Year 2, we said it costs $10,000 times 1.04 times 1.04, which we said equaled $10,000 1.04 squared. Okay, we want to find t years after 2012. So however many number of years after 2012, we don't know. But we want to find a formula for it. Okay. So if we think about this, make everything look the same. This has a 1 here. This has a 0 there. Year 0, 1.04 raised to 0 is 1. 1 times 10,000, 10,000. 1.04 raised to the first times 10,000 will give you year 1. 10,000 times 1.04 raised to the 2 gives you year 2. So what do you think gives you year t? Hopefully you see it. 10,000 times 1.04 raised to the t, right? That's a pretty simple formula. Now we said that B said graph the growth of the model found in part A, and we've got a range. And we're going to use a calculator to do all the rest of it. Now, essentially what this does, hopefully, I really hope you see this pattern. I hope you saw it. We've got one of these here, two of these here. If we're going to do it t times, we're going to have t of these. So we're going to have t of these 1.04s. So I don't know if that's going to be 1, 5, 1000, or 10,000. It could be every many of these as it needs to be. That's what that t represents. But instead of just multiplying a whole bunch of them, we're going to use that exponential function. So let's take it to the board and answer the rest of the questions. Let's graph this function. This function is 10,000 times 1.04 raised to the t. We're going to use x to represent t here. Now, it said in your problem, if I pull it up, it wants it to go from t equals 0 to t equals 13. So, x min of 0, x max 13. Let's graph that. Doesn't show up. If we use zoom and we use zoom fit, which is 0, you can scroll down or you can just hit 0, it will keep that x bound, but it'll expand the y where you can actually see it. So your x here, if you want to check it, double check your window, your x is still from 0 to 13, but it stretched your y so that you can actually see your function. So here's our function. We got it from 0 all the way to 13. It increases, which is clear and expected. Now, what we need to do now is answer part C. It says if an item costs $10,000 in 2012, use the model to predict its cost in 2025. How many years after 2012 is the year 2025? Let's use our calculator. No need to take this to the board. 2025 minus 2012 gives us 13. So the t we're going to use is 13. If I can go to my graph, I can do second calc, value, x equals 13, because x is what we're using for our placeholder for t. And it'll tell me that my y equals 16,650.735. If you don't like that method, you can also do second table. And you could scroll down on your x to x equals 13, and you'll see it rounds, but if you scroll over here and put your cursor over top of the number, it gives you the full number on the bottom where it's not rounded. It gives you 16,650. Here it rounds it up to 51 because it can only fit so much in that small space. So that would be the answer to part C. The answer to part C would be 16,650.74. Easy enough. Okay, so the next example says total personal income in the United States in billions of dollars for selected years from 1960 and projected to 2018 can be modeled by y equals 492.4 times 1.07 to the x, with x equal to the number of years after 1960. What does the model predict the total U.S. personal income to be in 2014? We can do this one completely with the calculator. Okay, we need to figure out what x is. X is the difference between 2014 and our initial year of 1960. So let's do 2014 minus 1960. So we'll get out of this screen. We will do 2014 minus 1960. So the x that we need to use is 54. Easy enough. I can come back over here and I can say, okay, I need to use an x of 54. I've got two options. I can go ahead and graph this function if I want to, or I can just type 54 into this x, or plug 54 in for this x. We'll do both. So we got 492.4, 492.4 times a 1.07 raised to the 54. So the answer we should have should be 19,012.62311. Alright, if you wanted to, you could also take this same function. You could come over here on your calculator, go to y equals, clear the old function out, 492.4 0.4, I believe that's correct. Yep. Times 1.07 raised to the x. You could graph it, and it doesn't show up, so we will do a zoom fit on it as well. So 0 for zoom fit. Okay, it shows up. Now, the number that I wanted to find here was 54. We found that on our calculator from our regular screen. So you got a few options. You could go second table and scroll down to x equals 54, which would take you a while. You could go back to your graph and you could try to find it. You could go second calc, value, 54, but depending on how your graph is zoomed, it might not be able to find it. The reason being is the value has to be within the window. If it's not within the window, then it's not going to be able to find it. So you might have to go over here and you might have to adjust your window to include 54. I'm going to go ahead and back it out, say to 60. I'm going to graph, I'm going to zoom, fit again, see if it does a better job. There we go. Now I can do second calc, value 54, and it'll find it right there. Same number we had before. Okay, don't believe me? Hit second quit. It's right there. We found it before. So part B says graphically determine the year during which the model predicts total U.S. personal income will reach 28.5 trillion. Okay, if I come over here to my calculator, I hit graph. I've got the graph here. Pause it. Alright, I interrupt this problem to remind you that this problem is in billions of dollars, and it asks us to find when we'll hit $28.5 trillion. Billion, trillion, not the same thing. Okay, so what we're going to have to do is we're going to have to adjust. Okay, how many billions is 28.5 trillion? Okay, so let's think about this. Okay, that's 100. That's 100,000, right? That's 100 million. Okay, that would be 100 billion. Oh, so a billion is 1, 3, 3, 3. This is 100 billion. This is 1 billion. Okay, after 100 billion is 1 trillion. That is 1 trillion. We need to get 28.5 trillion into billions. Okay, so we wrote 28.5. That point's going to become a comma. Okay, so we got 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. Right? Because hundreds, 100,000s, 100 millions, billions, 100 billions, trillions. So, how many billions is 28.5 trillions? Well, the billions is after 1, 2, 3 sets of zeros. 1, 2, 3. So, looks like 28.5 trillion equals 28,500 billion. So, easy enough. 28.5 trillion equals 28,500 billion. Okay. So, let's get back to the problem and use that 28,500 billion. All right. So we know to look for 28,500 billion because we have converted. So we're over here at the graph. Okay. If I hit second calc and I type in value, it's not really going to do me any good because the value that it searches for is your x value. So, easiest way that I know to do it, we're looking for 28,500 billion. Type that in Y2. Hit graph. It's going to graph it way up top. Then you're going to do second calc. Intersect. Okay. First curve, second curve, and then you're going to try to estimate where they hit. So I'm going to let it go over here. Hit enter. It tells me that they intersect at 59.98 for your X and 28,500 billion. Okay, so approximately 60. So 60 years after 1960, because 1960 is our initial year, is when we'll reach 28.5 trillion. So 60 is not what you would use for the answer. You have to come over here to your calculator, or you can do it in your mind. You have to do 1960 plus 60. So your answer will be 2020. That would be the answer to the problem that you would use. You would not use 60, you use 2020. Obviously, I don't think we're going to hit that this year. Got some coronavirus going on, really hurting people's stocks, people's work, all that kind of stuff. Not so sure that we're going to have personal income at 28.5 trillion. But you never know. You never know. Stay in college, it pays. If we scroll on down, what we're going to look at now is exponential decay models. Okay, so we looked at exponential growth. Now we'll look at exponential decay. So the equation we have is y equals a times b raised to the kx, where b is greater than 1, a is greater than 0, k is less than 0, or y equals a times b raised to the kx, where 0 is less than b is less than 1, a is greater than 0, and k is greater than 0. We don't have an x-intercept. Our y-intercept is 0a, just like it was in the exponential growth model. The domain is all real numbers. The range is all real numbers, where y is greater than 0. Horizontal asymptote is still the x-axis. The shape is decreasing on the domain and concave up. So, if we look at this example, it says it pays to advertise, and it is frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. The decline in sales is called sales decay. Suppose that the decay in sales of a product is given by S equals 1,000 times 2 raised to the negative 0.5x dollars, where x is the number of weeks after the end of a sales campaign. Use this function to answer the following. What is the level of sales when the advertising campaign ends? B says, what is the level of sales 1 week after the end of the campaign? C says, use a graph of the function to estimate the week in which sales equal $500. And D says, according to this model, will sales ever fall to 0? Alright, let's get to answering these, starting with A. Alright, so if you read the question, and you really read into the question and understand it, it's asking on part A, what is the value of the sales after the end of the campaign? Okay, as soon as the campaign ends, that's when x equals 0. So the initial week that it ends, x equals 0. If I plug 0 in here, anything raised to the 0 is 1. So I get 1,000. Just gonna plug it in. Oh, sorry. 0 goes here. So anything raised to 0, 0.5 times 0 is 0. 2 raised to 0 is 1. So at the end of the advertising campaign, sales is $1,000. Week 1 for part 2. This was A. Week 1, all you're really doing is you're plugging 1 in for X. Right? Now, I'm going to go to the calculator we're going to figure out exactly what this number is for week 1 for part B. Alright, so if you type it on the calculator, 1,000 times 2 raised to the negative 0.5 times 1, you get 707.1067, and you'll round appropriately. If it tells you to round to 2 decimal places, it'll be 707.11. Easy enough for part B. Part C says use a graph of the function to estimate the week in which sales will equal to $500. Okay, so let's come over here. We've got the function. We're going to type it in. Let's clear all the old stuff out. We've got 1,000 times 2 raised to the negative 0.5x. Okay. I'm going to do zoom. Let's do, I don't know, zoom fit again, see what happens. Okay, that's a pretty decent function. You can see it's increasing, it's concave down. So, what we've got here, we need to figure out when sales equals 500. So, sales is going to be your y, because your x is the number of weeks. Sales equals 500. I'll type y2 equals 500. I'll graph it. Wherever they intersect at will be your answer. Second calc, intersect, first curve, second curve, and I'll scroll over here to where they intersect at. So they intersect at x equals 2. X equals 2, y equals 500. Therefore, in the second week is when your sales will drop to 500. Easy enough. So 2 weeks after your promotion ends, your sales drop from initially being 1,000. 2 weeks later, they will drop to $500. Okay, so that answers part C. Alright, so if we want to answer this part D, will sales ever fall to 0 according to the model? Go second calc, look at the model. Don't have to do second calc, just graph it. Hit trace, not second calc. Make sure you're on the right function. We are. So you can change functions by going up and down if you need to. We're on this function, the function we're actually looking at. We want to know, does it ever actually go to 0? Okay, so our x is the number of weeks after the sale. Our y is the number of sales. So if you'll notice, while it gets really, really close to 0, it doesn't actually hit this x-axis, because the x-axis is the asymptote. It just gets really, really close to it. So does it ever go to 0 according to this model? No, it doesn't. It gets really, really close to 0. It gets essentially at 0, if you're thinking in money terms, but it never actually reaches the technical 0. If we continue on to page 6, next example says, if $10,000 is invested for 15 years at 10% compounded continuously, what is the future value of the investment? Let's take this one to the board. Alright, so we're compounding continuously here. So hopefully you've seen the compounded continuously formula before. If you haven't, here it is. I'm going to explain our way through it. A is the amount that you make. P is the principal, which is the amount that you invest. E is a mathematical constant. Okay, I'll show you where to find it on your calculator if you've never found it on your calculator before. R is the rate of interest. T is the time in years. That rate of interest has to be in a decimal. So, if we use it in our problem, the amount that we're going to earn, A, equals the principal that we invested, $10,000, times E, raised to the R. Our rate of interest was 40%. 0.40, that has to be in a decimal. And we're investing it for 15 years. That's it. All we've got to do is type 10,000 E raised to the 0.40 times 15 into our calculator, and we will get our answer. Alright, so let's do it. 10,000. Oops. 10,000 times. If you need to find that E, you have a few options. Okay, the easiest one to use for this one, since it's E raised to something, is the second natural log button. If you just want simply an E, you can also do second divide and it'll give you just an E by itself. So we've got E raised to the 0.40 times 15. If we hit enter, what we wind up with is 4,034,287.935. So quite a return. Quite a return. Normally you don't get a 40% interest rate if you invest something. If you find something that has a 40% interest rate, please let me know. I would love to invest and get 40% return. But that is how the compounded continuously function works. Okay, simple formula. Most people call it the PERT formula, P-E to the R-T. Answer to the question. If you look at it, what you would write here, it just wants to know what the future value of the investment is. Future value of the investment would be, like we said, 4,034,287.935. That would be the answer to this one. Okay, now let's look at the next example. During the life of an organism, the ratio of carbon-14, C14 atoms to carbon-12 atoms remains about the same. When the organism dies, the number of carbon-14 atoms within its carcass begins to gradually decrease, but the number of C12 atoms does not. So they can be measured to determine how many C14 atoms were present at death. The number of C14 atoms in an organism, when it is discovered, can then be compared to the number present at the time of death to find out how long ago the organism lived. The ratio of the present amount of C14 to the original amount is given by Y over Y naught equals E raised to the negative 0.0001297t, providing us with the function that Y equals Y naught times E raised to that large negative exponent. So that gives the amount remaining after T years. If the original amount of carbon-14 present in an artifact is 100 grams, how much remains after 2,000 years? The easiest way to do this is to take this and type it in your calculator. Okay, got my calculator here. I'm going to put this here, put that there, so that I can see it, typing it in, and then I'll make the calculator a little bit bigger. I'm going to do it in my Y equals. Okay, I know you can't see this really well now, but I will expand it. All I'm doing is typing this function in. Okay, so the Y naught in our formula that we're going to use for part A is that 100 grams. So 100 grams is going to go where this Y naught is. So I've got 100 times, I'm going to do second E raised to the negative 0.1230 12097t, and we'll have to use an X for our T. So I've got it typed in. We want to know how much remains after 2,000 years. Okay, so I've got it typed in here, right? That's all I did on this little small screen. I blew it up so that you can see it. Now we want to figure out after 2,000 years, right, what our value is going to be. Okay, so this is where you have to know your function. We're using X to substitute for this T here. Okay, years goes where the T's at, so it goes where the X is at. So if I come over here to my calculator and I graph it, I'm going to do a zoom fit and graph it. Hopefully I see it enough. If I do second calc value, let's do value, not 0, value 2,000. If I hadn't gone 2,000 out on the X, it will shoot back an error, which it does. If I go to window, X max, oh yeah, 2,000, let's do Let's do 2001 to make sure I get far enough. I'll do zoom fit after that. Now I can do second calc value 2000. Okay, so it finds it for me. It says, okay, at x equals 2000, y equals 78.51. So your answer there would be 78.51. Alright, if you're having trouble with your calculator doing the exact steps that I did to get where I've gotten, the other way you could do it, second quit, you could just pull up the function that we had. So we had, I believe it was 100 for our y naught. Yep, 100 for our y naught. So you could just type in 100. We could do e raised to the, and then you'd have to type that negative 0.123012. Trying to remember what the number was. 097. Okay. X here was what, 2000 that we were plugging in for it? Yep, 2000. Then you wind up getting the same thing, 78.51. Alright, B is a little trickier. B says, what percent of the original amount of carbon-14 remains after 4,500 years? So, we're talking about a percent here. So, this is actually where this function is going to come in handy. So, we've got this y over y naught, which will give us a percent, equals this e raised to the negative 0.0001297t. Okay, even says the ratio. Okay, so if I want to figure out how much of the, or what percent of the original is left after this 4,500 years, I don't know what y naught is for B. So what I'm going to do is I'm just going to plug 4,500 into this piece right here, and it'll give me that ratio or that percent or that decimal that can be converted into a percent of what's remaining. So let's do that. Go here to the calculator. We will do second e raised to the negative 0.0001297. Alright, times that 4,500. So, approximately 58%, because we get 0.58021 on down, approximately 58% of that original carbon-14 remains after 2,000 years. Or after, sorry, 4,500 years, looking at part B. So, after 4,500 years, approximately 58% of that carbon still remains in that organism. That completes 5.1. I'll have a lecture up for 5.2 shortly. Y'all stay tuned for that and get a chance to watch that as soon as you can. Let me know if you have any questions, and I appreciate you watching.